After practice worksheets 12A, B, and C, before we move on to the topic that using the Morse circles to do the stress transformation, I just want to have a summary of stress transformation and stress block. Stress transformation and stress block summary. Yes, basically we have the note in the previous video. Just want to summary so that we have everything in one place. Equation that we have previously, to given sigma x, sigma y, and tau xy, we can be able to determine the normal stress in a plane x apostrophe, so sigma x apostrophe in the axis x apostrophe, rotation and angle theta from the x axis or x plane, that we will have sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine 2 theta, and then tau xy sine 2 theta. This equation, nothing new. We already have in previous notes and videos. And of course, the associated shear stress on the x plane direct to x apostrophe plane and direct to y apostrophe axis. Remember, the plane is defined by the axis perpendicular to that plane. It equal to negative sigma x minus sigma y divided by 2, and then sine 2 theta plus tau xy cosine 2 theta. And from that, we can draw the blocks when we do that transformation in terms of stress block. With the block, original blocks, we have from a general analysis, general loading, we have the normal stress sigma x, and then we have tau xy, and of course in opposite to be equilibrium we'll also have that a sigma x, and the tau, it will be going down to make it counterclockwise rotation, and then we have sigma y opposite, and then to make equilibrium we need the other tau, and it's the same as tau xy, but if you recall that we call it tau yx. So there are two components, y tau xy. X stands for the shear stress on the plane that we define, and the plane here is let me write down here so that we can use either x plane. Okay, so the plane is defined by the axis perpendicular to that plane, and more specifically that is the positive, and the left side it will be the negative x plane. And then this one, the one here, that plane, we call that is the y plane. So plane defined, like I say, defined by the axis perpendicular to that plane. So in y plane, it it parallel to the axis, not vertical, as you can see there. So that it explain, and that the two positive explain that you have it in blocks. Now if we transform that to another plane, that by rotation the block to another cut, as you can see, like let's worksheet 12C. So let me write that. If instead of original coordinate x and y, if the block become from an angle theta from the original plane, so with that, how we define the theta? Theta defined from the original plane to the new plane. So let's define that here. That is original x plane, as you can see, that green one, original x plane. Now the plane it go that way, then the theta, that basically a theta we are talking about, that is the theta, angle theta from the original plane to the new plane when it rotates. So from that one, the vertical is the x plane, as you can see here. So from that we have the axis and associate normal stress go that direction is the sigma x apostrophe, because that from the vertical x plane rotate angle theta, and in this case counterclockwise. And then you also have the associate on that plane is the shear stress, and that is tau x apostrophe, because that on the x apostrophe plane direct to the y apostrophe axis. So you have that. And here similarly, that one, if you know that it already x apostrophe, then this one it have to be sigma y apostrophe. And go ahead to complete the stress block. If the tau xy on the positive x apostrophe plane it go up, then that one go down. Sigma x apostrophe on this negative side, it will be go opposite and same magnitude. And then similar tau, this one is tau y apostrophe x apostrophe, and that the same magnitude for the tau x apostrophe and y apostrophe. Similarly, we have the negative plane in here, tau and sigma y apostrophe. If you want that, it will be the same, right? And here sigma x apostrophe. So that is the equation for the stress block and stress transformation. Now we also talk about the principal stress. So let's talk about that summary too in terms of the principal stress. Principal stresses equation. Suppose we already know that principal is, we got sigma 1 and sigma 2. The equation is sigma 1, sigma 2 is equal to sigma x plus sigma y over 2 plus minus, because we have 2, sigma 1, sigma 2, 2 principal, then square root of sigma x minus sigma y over 2 square plus tau xy square. And at the principal stress, we have tau on the principal stress in that equal to 0. And when we determine the principal stress and what is the stress block in that case, you can see if we have a block to find out the principal stress. So let's draw the block here. And then on the plane, it rotates an angle. And that angle here, when it get the principal stress, then that we call it, everyone remember what we call theta p, that theta p. And for the principal stress, that theta p, so that is will be the first principal stress sigma 1, and of course the opposite will be the same, and in this case I assume it in tension, it can be in compression, and then the one, let's assume the sigma 2 in this case is in compression, sigma 2 for there, and no tau, okay? And then the equation to determine the angles for the principal stress, and we have two roots if you recall. Tangent of 2 theta p is equal to tau xy divided by sigma x minus sigma y over 2. So that is the principal stress. Let's go to the last summary. We find out the maximum normal stress and minimum normal stress at that location, and that tau equal to 0. Now we also want to know, okay, which plane we have the maximum shear stress. So that is the next summary that we want to write down. So maximum in plane shear stress. Why it in plane? Because the shear is always on the plane that we cut, tangent to the plane. In plane shear stress. And for that we have the tau max equal to, again, just make a summary so that we can have an overall picture before we move on to the Morse circle. Sigma x minus sigma y over 2 square plus tau xy squared. And it also equal to, or if we use the principal stresses, then we have tau max equal to sigma 1 minus sigma 2 equal to. And at tau max, at the plane that have tau max, the normal stress is sigma average. So sigma average on that plane equal to, as average by that name imply, and you can see it will be sigma x plus sigma y over 2. That is sigma average. And the plane to define the maximum stress, we call it theta s, as you have it previously in maximum in plane stress. So what theta s, what we can find out in here, so that defined by the tangent theta s, and let me write down what angle we are talking about for theta s. So if the blocks here have a plane that have a maximum in plane shear stress, so what do we have? It rotates the angle, and that angle we call it theta s, so that the angle theta for the plane from the original coordinate or original plane that have a maximum in plane shear stress. So with that maximum, so the shear stress on that plane tau, it becomes tau max. And of course from that we can know that opposite and have to be go here to make the block in equilibrium. Unlike the principal stresses, you don't have tau in that block, but for the maximum in plane shear stress we have the normal stress sigma, and that is sigma average. So we have here sigma average, sigma average, sigma average, and sigma average, and that is theta s. How to determine the theta s? It's basically similar to the theta p. We can determine by equation here, and then you inverse tangent, so you can find out theta s. And keep in mind tangent of 2 theta s, not 1, equal to negative theta x minus sigma x minus sigma y over 2 and divide by tau xy. So that is the theta x, and from that inverse tangent you can find out theta. So that basically the summary for what we have so far in terms of stress transformation. And you can see this class very abstract, so focus on this one here. And then let's move on to the Mohr circle that we use the other method to solve a similar problem that we use with the equation just mentioned here.